In this module, we will look at containers. You'll learn what containers are, how they differ from virtual machines, the importance of containers in cloud computing, and the benefits they provide. The tech community is abuzz with words like containers and containerization. This technology has grown immensely in recent years, and it's poised to continue that growth in the years to come. This course is dedicated to teaching you all about containers. So what exactly is a container? A container is an executable unit of software in which the application code is packaged, along with its libraries and dependencies, in common ways so that it can be run anywhere, whether on a desktop, on-premises, or in the cloud. To do this, containers take advantage of a form of operating system virtualization, in which features of the operating system are leveraged to both isolate processes and control the amount of CPU, memory, and disk storage that those processes have access to. In the case of the Linux kernel, namespaces and C groups are the operating system primitives that enable this virtualization. Containers are small, fast, and portable because unlike a virtual machine, they do not need to include a guest operating system in every instance and can simply leverage the features and resources of the host operating system instead. Containers first appeared decades ago, but the modern container era began in 2013 with the introduction of Docker. Given their name, shipping containers serve as a useful analogy for the containers that we talk about in this course. The shipping industry originally lacked a standardized way to ship goods. As you can see in the first picture, this lack of standardization resulted in a less optimized and more arduous shipping process. To remedy this situation, shipping containers were introduced to standardize the way things are packed and shipped. Now, the only thing that can go on a cargo ship is a container. Anything that fits in a shipping container can be shipped. By standardizing, shipping became much more predictable and optimized. The containers we're talking about in this course are much the same. They are a standardization for how we package and ship software. All the dependencies needed to run an application are packaged with it, making it easy to move it around and run it in a variety of locations. Just as you can ship anything that fits in a container, modern platforms for running containers can run anything as long as it can be packaged as a container. This portability is incredibly useful in software development. The primary advantage of containers, especially compared to a virtual machine, is the level of abstraction they provide that makes them lightweight and portable. Containers are lightweight. They share the machine operating system kernel, eliminating the need for a full operating system instance per application. This makes container files small and less taxing on resources. Their smaller size, especially compared to virtual machines, means they can spin up quickly and are better able to support cloud-native applications that scale horizontally. Containers carry all their dependencies with them, meaning that software can be written once and then run without needing to be reconfigured across laptops, cloud, and on-premises computing environments. This portability also provides consistency in your environment so that you don't have to worry about differing dependencies installed in different environments. The combination of their deployment portability and consistency across platforms and their small size makes containers an ideal fit for modern development and application patterns, which expect regular deployments of incremental changes. Like virtual machines before them, containers enable developers and operators to improve the CPU and memory utilization of physical machines. Containers go even further because they also enable a microservice architecture, which means that application components can be deployed and scaled more granularly. This granularity provides an attractive alternative to having to scale up an entire monolithic application when, for example, a single component is struggling with load. Virtual machines provide a useful comparison with containers and help us understand the appeal of containerization. With virtual machines, a hypervisor runs on top of your infrastructure. This hypervisor is responsible for creating virtual machines. It treats resources such as CPU and memory as a pool that can be utilized by the various virtual machines running on the hardware. In this model, the hardware is virtualized so that multiple machines with potentially different operating systems can run on the same physical hardware. As the diagram shows, each virtual machine has its own operating system. In addition, binaries and libraries are present in the virtual machine, which enables the execution of applications. With containers, you still have physical infrastructure at the bottom of the stack. But instead of placing a hypervisor as the next layer to virtualize the hardware, you have an operating system. Above that is the container engine, which, like a hypervisor with virtual machines, is responsible for running containers. In this way, containers virtualize the operating system rather than the infrastructure. This enables the infrastructure to have a single copy of the operating system, which saves a lot of space. The binaries, libraries, and applications run on the container engine. The clear benefit of containers is that you do not have to run a dedicated operating system instance for each virtual environment. Instead, one operating system is virtualized across all containers. This enables containers to be much more lightweight than virtual machines. While virtual machines can take several seconds or even minutes to start up and can be many gigabytes in size, containers can be only a few megabytes and start in mere seconds or less. Containers are becoming increasingly prominent, especially in cloud environments. Many organizations are even considering containers as a replacement for virtual machines as the general-purpose compute platform for their applications and workloads. But within that very broad scope, there are key use cases where containers are especially relevant. Containers are small and lightweight, which makes them a good match for microservice architectures where applications are constructed of many loosely coupled and independently deployed smaller services. The combination of a microservices architecture and containers is a common foundation for many teams that embrace DevOps as the way they build, ship, and run software. Because containers can run consistently anywhere, across laptop, on-premises, and cloud environments, they are an ideal underlying architecture for hybrid cloud and multi-cloud scenarios, where organizations find themselves operating across a mix of multiple public clouds in combination with their own data centers. Finally, one of the most common approaches to modernizing applications is to begin by containerizing them so that they can be migrated to the cloud. Congratulations on finishing the first video in this course. You should now be familiar with the concepts of containers and containerization. Specifically, you should understand what a container is and how it differs from a virtual machine, as well as the benefits that containers provide in software development. In the next video, you'll learn about Docker and its contributions to containerization.